In the previous video I was talking about vector quantization, and in this video I'll be talking about transform vector quantization. So what is transform and what are the advantages that it gives with vector quantization? That is what I'll be discussing it in this video. First I will take the word transform and I'll explain this terminology. Transform is nothing but transforming the data in one domain to another domain, say from domain X to domain Y. When I transform the data from domain X to domain Y, I call it a forward transform. When I transform the data back from Y to domain X, then I call it as a inverse transform. For example, if I have some data in time domain, say all values are analyzed with respect to time, then I want to transform it to frequency domain. Most of the time the analysis is done in the frequency domain because of the advantages that we get in the frequency domain. Most of the example is the signals are analyzed in frequency domain. They are transformed from time domain using the Fourier series to frequency domain, and then they are analyzed, and if required we transform back to time domain using inverse Fourier series. So this transformation from time domain to frequency domain using Fourier series is called, can be told as forward transform, and the opposite of that using inverse Fourier series is nothing but inverse transform. So why did I talk about the transformation here, maybe the time domain to frequency domain? What is it that we achieve with respect to vector quantization? I have a volume which has data values. So let's consider I have some data value and I want to transform it to the frequency domain. So in case of the volume data, I will do the transformation using maybe a discrete cosine transform. This is the forward transform. If I want to do the inverse transform, then I will use the inverse discrete cosine transform. Now what is the fun in transforming to frequency and then getting it back to the data value? Where can we apply vector quantization? So there is advantage of applying vector quantization here. In the previous video we were applying the vector quantization at this position, that is directly to the data values, but now we will use vector quantization in the frequency domain, and we will see the advantage what it gives by using vector quantization in frequency domain. As we can see, in the frequency domain the data is organized into high frequency data, that is the white part is the high frequency data, that is the data in this side is a high frequency data, and the blue part is the low frequency data. So how will I utilize this in my compression technique? I will give a brief idea of how I will compress the data using vector quantization and transformation. So this is the big picture of what I will be doing. I have the original data which I use the forward transform on it, and then I'm going to use the concept of high frequency and low frequency data. That is, I do a classification of data. I just copied the figure, that is, this is the same block, but I will take the low frequency data and I call it as a low pass partition, and the medium frequency data as a band pass partition, and the high frequency data from here as a high pass partition. So you can see this part is nothing but the low pass partition, that is the low frequency data, and the data here, this part is here, and the medium frequency data here is in this. So this is basically the same image. For explanation, it has been separated into 3 figures. It's the same volume data, and then I use vector quantization, that is the compression, and from the compressed data, assume this is the compressed data, I will use, after compression, I use the inverse transform. So the forward transform is applied here, I will use the inverse transform. Then again it will be in the form of data values. So it's in the data domain. This is in the data domain. This is in the frequency domain. This is divided into different frequency bands and then compressed, and this is compressed data, but it is in the frequency domain. After applying the inverse transformation, I get data domain, and in the during rendering, what I do is simply take the compressed data in the data domain and do the decompression, decompress the data, and then display the data on screen, that is volume rendering. So let's say I have a data of 100 GB, oh sorry, 1 GB, then I transform it into the frequency domain. It is also 1 GB. This whole thing is 1 GB, and then after vector quantization, assume that I have 600 MB because it is compressed data. Now I have data of 600 MB. This data I will be using for rendering here. The 600 MB data is decompressed and used for rendering and displayed on the screen. Now, why did I classify the data into 3 parts, that is low pass partition, band pass partition, and high pass partition? That may be the question that is in your mind. So why did I do the classification? This is what I achieve from transforming the data from the data values to frequency domain, because it is easy for me to classify the data. Now what is the advantage of classifying the data? Let us consider the normal scenario where I have the data and I use vector quantization and I have the compressed data. As you know, vector quantization is a lossy compression technique. So here I will lose some data, so the visual quality decreases. Visual quality decreases after, this is decreases after compression. So to overcome this disadvantage, what I do is I transform the original data to high pass frequency, high band pass frequency, and low pass here, and compress them at different rates. Like high pass frequency, I compress them at 10%, band pass frequency, I compress them at maybe 40%, and low pass frequency I compress them at 90%. So by doing this, what I achieve is better visual quality. Better visual quality. You may ask, why do I achieve better visual quality by compressing at different rates? Even here I have compressed at 90%. I have compressed only the low frequency data at 90%. High frequency data I have compressed at 10%, that is lesser than what I have done for low frequency data. But you may ask, why did you compress low frequency data at higher rates? The low frequency data does not give much effect to the visual quality, even if it is there or not there, does not affect the visual quality. But high frequency data is something like the edges in the image. Edges in the image is actually the high frequency data. So if the edges are blurred, then the image looks bad. So the high frequency data is collected, that is all the edges are collected in the high frequency components, high frequency partition, and in the low partition the common area, it's this part, maybe all are white, so all these are collected in the low partition. So if I compress them at 90%, it does not matter whether this point and this point are compressed and are occurred at lower quality. You may not observe it, but if the edges are bad, then the visual quality is clearly visible that it is decreased. So by classifying the data, I get a better visual quality after compression. That is, if I compress this at lower rate and this at higher rates. So I think now the big picture should be clear. So I'll again explain the big picture, what I am doing. So I have data, I will forward transform the data and bring it to the frequency domain. In the frequency domain, I will have high frequency data, the high frequency data and the low frequency data. The high frequency data is at my mouse is not moving, I don't know what is the reason. So the B block is the transformed block,